I will present another application, a wonderful application of UHPC. This time will be in a slab beam superstructure systems, talking more specifically about the cyclic and strength performance. So the outline of this presentation, I will briefly talk about what the slab beam is, the FSB system and UHPC, the research objectives, joint and section development, joint testing, full-scale beam testing and implementation. So talking about the background, slab beams have been used in construction since pre-stressing pretty much began in the US in the mid-50s. There has been several iterations, and with those iterations, there has been several connecting mechanisms, like you can see here, transverse tie bars in sleeves, grouted shear keys, etc. However, as Dr. Haber mentioned earlier, at piano, keyboard behavior, there have been some issues observed with previously used slab beams. Here is one highlighting the longitudinal refractive cracks that occur in the superstructure due to the differential deflection of the beams. However, poor performance of previous systems led to the development of alternate systems. Here are two examples of them: the precast composite slab span system, or PCS, from Minnesota, and here Florida Slab Beam system in 2015. They both share similarities. They both have bottom lips so that you don't have to include bottom formwork in the system when you cast the deck on top, and they have reinforcement running along the joint system. Ultra high performance, the solution we want to do is to replace the casting place deck and the connecting mechanism that you saw before, use UHPC only in the joint, the closure pore. UHPC is well known for their properties. It's high compressive strength, tensile cracking strength, and higher modulus of elasticity. Here are two examples, typical compressive and tensile, figure A and figure B, UHPC behavior. And also you can see on the far right, some examples of the measured compressive and tensile strengths we got in the testings for different UHPC batches. It has been included in different applications, such as overlay, was previously talked, and also even developing sections itself, precast prestressed girders and waffle slab systems, for example. The research objectives was to develop a cross-section in joint region detail for short to medium span bridges for use with accelerated construction, and assess the strength and cyclic performance of cross-section and joint, and recommend them fabrication procedures, on-site construction practices, and erection tolerances. To develop the cross-section, we started first with a joint testing program, or a small-scale scenario, where we tested out different joint configurations and geometries to come up with the best solution to increase the strength performance of the system in the transverse direction. So we compare the original slab beam with casting place deck. The first group on the left, they were 18-inch thick slab, and the group on the right were 12-inch thickness with different joint geometries configurations. This is a test setup we came up with, basically following guidelines that the Federal Highway Administration did to box girders. This is for the small scale, and we apply basically a 3-point bending test where we put or exerted the load using a wheel patch geometry adjacent to the joint region so that we could create shear and moment at that joint boundary specifically. Some brief experimental results: the ultimate capacity, pretty much all of them perform similar or better than the original FSB detail, and we come up with the best performance of 18A1, which is the kind of diamond-shaped keyway detail. Same thing happened for the 12-inch deep specimens. Here, the lower the joint reinforcement was located, the better performance we got in the UHPC joint. So in that case was the 12A2, and also we exerted cyclic performance here in this group, and the cyclic did not alter that much the strength performance, as you can see on the far right bottom graph, the load versus deflection. So talking about the full-scale beam testing, that we come up with a section that we decided was the best performer overall, the small scale. we came up with 3 testing phases. Phase 1 using 2 beam configuration, phase 2 using also 2 beam configuration, and phase 3 using 4 beam configuration, pretty much almost the full superstructure width. In this presentation, I will just talk about phase 1 and 2, the 2 beam configuration. The only difference between them two were the type of loading and the boundary conditions we use for them. The beam design was pretty much based of a 2-lane bridge with 6 slab beams and 28.9 span length. So the beams were 30 feet long and they were 12-inch deep FSB sections with 14.6 inch diameter strands. And you'll see the strand pattern there. The shear and confinement reinforcement was based off the current FSB standard with the slight modifications because the current FSB has the shear reinforcement protruding from the top of the section because it's designed to act in composite action with a cast in place deck. However, here we don't have the cast in place deck, we don't have to protrude the reinforcement. Also, their joint reinforcement and the geometry was based from the small scale testing. Here is, I'm showing the joint A2 with the geometry and dimensions of the rebars. And it was designed following the Federal Highway Administration guidelines, design and construction of field cast UHPC connections. They were built offset so that we can just design one beam and then rotate the beam when we wanted to put them side by side. The beam design and regions also was designed based on AASHTO, including the confinement, reinforcement, ledge reinforcement, and bursting steel reinforcement. So here are a few pictures about the beam construction. So 2 beams were constructed for service and strength testing. That was for the first testing stage. And then we built 6 beams for the second testing stage. You'll see the cage reinforcement, the concrete pour, and the paste retarder we applied to the sides of the slab beam system, and then the removal of with pressure washing of the paste. We also use software, Athena modeling, to model the different load configurations and different stresses that we wanted to see in a real case in the lab, and come up with the best or the most efficient way to get the most results for us that were investigating this behavior. The loading was based on either half or full axle HS20 struck. The half side is red and full axle will be the blue one, the blue square. The static load configurations, 2 static loads were developed where we apply a full width rear truck axle load at the midspan, and then half axle, kind of extending what we did in the small scale scenario. Also, during phase 2, we experiment with continuous, or try to impersonate a continuous connection by restraining the rotation of one end of the system, as you can see here in the system, in the figure. Phase 2 also had fatigue performance or cyclic performance, 2 testing configurations. Reverse sinusoidal was applied to in FC25 and FC26. We restrained the deflection of one beam while we exerted the cycles on the other beam, kind of trying to crack that joint at the boundary region with the different loading configurations you see here. Over 4.7 million load cycles were applied to the 2 beam systems in phase 2. An additional cracking load protocol was also used because we impersonate one crack by sawing the boundary between the UHPC and the precast section. So here are some observations. The joint performed well during service and strength testing in both phases. No joint debonding or distress was observed throughout testing of both 2 beam systems, and good transfer of stress between beams. So basically, we exerted the ultimate capacity during phase 1. And after 4.7 million cycles, ultimate capacity again, and we compare the 2 results. And you'll see on the graph on the right, the load versus displacement, pretty much the difference is 2%. So the system hold good. FIU 4 and 5, this is the 2 beams for the second phase, had similar performance to FIU 1-2 during ultimate strength testing. 4.7 million cycles and other service loads and cracking tests did not impact the overall system behavior. So you'll see here that we had crack displacement transducer to measure the opening of the joint region and the strains there for the testing phase number 2 and testing phase number 1 was below 60 microstrain. Also, testing phase number 2 had several cycles, 4.7 million cycles. We didn't observe any decay in the strain performance. The transverse tensions in precast beams and across joints remain below estimate cracking strains on top and bottom of system for all service tests, even after the 4.7 million cycles. However, we remember that we exerted the saw, impersonated the crack of the UHPC joints, and that's why on the far right graph, you'll see reaching that strain gauge transverse, the strain reaching the tensile strain of the concrete. The joint demand, this is a detail that we observed in the system that was locked in the rotation on one end, measured using transverse cracking strain gauges, concrete displacement, crack displacement transducers across the joint, and reverse strain gauges also that were located in that joint region at midspan, decrease when a moment restraint was provided on one end, on FIU 4 and FIU 5. So here's the comparison that we observed for those gauges when we had the restraint and when we didn't have the restraint, it was simple supported. A small compression strains, less than 15 microstrain, were measured in service and fatigue load configurations. Large tensile strains, also larger than 300 microstrains, were measured during strain testing. LC21, this is for phase 1, but remain less than yield strain. So the rebars were engaged, but they did not crack when the ultimate capacity test was performed. Also, we took cores at 3 key locations, basically at midspan and right adjacent to where the patches were. And this is where the location, west and east, sorry for the typo. And no signs of bond deterioration between joint reinforcement and UHPC in joint in any fatigue service or strain testing. However, we highlighted some cracking that occurred here, and we concluded that those cracks happened after the ultimate failure of the system. Some observations from construction, design forms, and joint construction of larger scale specimens. We noted that this is a very important step of the design, the construction of the joint, because we want to make sure that the formwork is perfectly straight along the length of the joint, and so that we don't have gaps closing or expanding when you put the two beams side by side. The pressure wash of the concrete cover was executed a day after casting, the 2 days after the casting, and the finalized exposure that you see here was the one we obtained. Also, the joint reinforcement length, we observed some variations of the rebar. We want to make sure that those rebars are approximately the same length. However, we didn't see any impact in the joint performance due to this small variation, even though some of those rebars had to be cut in the lab before joining or casting the joint. And the retarder finishes, you can see here light penetration. We did some mock-ups before doing the actual, constructing the actual joint. We got light penetration of 1/8 of an inch, and then medium light penetration of 1/4 inch, and this is the one we use for the final test. Observation from joint casting, the joint surface preparations. Mr. Perry mentioned saturated surface dry condition is necessary before casting the UHPC, because if this concrete is dry, it will absorb the water of the UHPC and the bond won't be developed efficiently. Also, the joint formwork is very important. We put plywoods here on top, 1/4 inch thickness, so that we can get that over pour. And then a day after, when we remove the formwork, we cool grind the UHPC of the overpour and even out the surface. And that's the final joint finish. So final implementation and to conclude the presentation. So here are some of the span ranges we can use the system and approximate number of strands. This is based on a 2-lane configuration bridge, sorry. You'll see a span from 20 to 55 feet, up to 55 feet. and the width of the beam 48 and 60 inches. And you'll see the thicknesses, and the number in parentheses are the numbers of strands that you will require to span this. However, if you want to go even longer spans, this will be non-standard sections because you'll end up with a very thick FSB section of 21, 24, and 30, and also 21, 24, and 27 for the 16-inch wide, and the amount of strands required to span that. And this is the final FSB design we concluded to have for the overall study with the joint geometry. Thank you very much.
Thanks to Dr. Chitty. Any questions from the floor or the audience? How many from the?
We don't have any online at the moment, but I see.
Yes, there is a question. Can you come to the mic, please? And in the meantime, I just want to mention one thing I noticed. We were talking about advertising schools. Did you see Dr. Chitty, how smart he was? The acronym of his samples were the acronym of the university. So very clever. Please.
I guess it's just a little question. I wondered if you had any issues coring, you were coring against two different kinds of materials. How is it to core UHPC?
It was tough. It was very tough, but we were able to core it down because it was just only 12-inch thickness. And yeah, it was done. So I think I can go back and show you, for example, we broke some cores here. You'll see this one is missing one piece and this one is cracked. That was under in the coring.
They end up with a lot of ribs in them because your coring equipment kept moving.
No, that I'm aware of.
Very smooth then?
Yes, it was very smooth.
Thank you.
Thank you. Maybe we have time for another question. Anything? Yes, sir.
Actually, if I missed it, but did you present the results of the final analysis, the model?
No, the models. Yes, I do have it. Yeah. The model, we use the model just to understand how the system will behave during the loading. We didn't compare per se the final results with the modeling we did before doing the test, because we wanted to see that the forces that we were going to exert to the system were within the limits of the lab. Yeah.
All right. Thank you very much.